driving along one of the most beautiful highways in America. And suddenly the road ahead is gone, not cracked, not damaged. That is the scenario scientists are quietly warning could become more likely along California's iconic Highway 1, where a newly identified 100-mile flood risk expansion near Big Sur is raising serious concern among experts who study coastlines for a living. Right now, something is changing along this stretch of coast, not in decades, not in theory. Now, satellite measurements, coastal sensors and terrain scans are showing subtle but accelerating shifts in water patterns, soil saturation, and cliff stability. None of it looks dramatic to the naked eye. Tourists still take photos, cars still pass, waves still crash. But underneath that calm surface, data is telling a different story. And what it suggests has scientists watching very closely. The discovery didn't come from a single storm or a single landslide. It came from patterns. Months of readings layered over years of historical records. Researchers comparing past coastal maps to present-day terrain models began noticing something strange. Areas that were once classified as low flood risk were slowly being reclassified, then reclassified again. What used to be considered a narrow vulnerability corridor began stretching 10 miles, 30, 50, until the risk zone extended across nearly 100 miles of coastline. Not because the ocean suddenly surged inland in one catastrophic event, but because conditions that make flooding possible started spreading silently along the coast, like a stain. The data showed increased groundwater saturation beneath cliffside soil. That matters because when soil fills with water, it loses strength. Imagine holding dry sand in your hand. Now imagine that same sand soaked. It slips. It shifts. It collapses. Now scale that up to cliffs hundreds of feet high. Researchers also detected subtle changes in coastal drainage patterns. Water that once flowed safely out to sea during storms is now pooling in certain low-lying stretches. That pooling increases pressure underground, weakening rock layers that support the highway above. At the same time, rainfall patterns in this region have become less predictable. Longer dry periods harden soil. Then sudden intense storms hit. Instead of absorbing water gradually, the ground rejects it, forcing runoff to move fast and violently across slopes. That combination is dangerous. Dry soil cracks. Heavy rain fills cracks. Water expands inside them. Rock shifts. And when rock shifts near a cliff road, stability becomes a question mark. Experts reviewing the data started using a phrase they rarely use lightly. Expanding hazard corridor. That phrase is why this story matters, because Highway 1 is not just a road. It's an engineering ribbon clinging to the edge of a continent, built into cliffs, suspended over ravines, balanced between mountain and ocean. When conditions change here, consequences don't stay small. This region has always experienced landslides. That's not new. But what is new is the scale of vulnerability being mapped. Sections once considered stable for decades are now being flagged for monitoring. Not closure, not evacuation, monitoring. That single word tells you everything. Scientists don't monitor places unless something about them demands attention. Why is this alarming? Because Highway 1 is a lifeline. It connects remote communities. It supports tourism economies. It carries emergency vehicles. It serves as an evacuation route during wildfires and storms. If even one major segment becomes impassable, detours aren't minutes long, they can be hours. And unlike inland highways, repairs here aren't simple. Fixing damage on a coastal cliff road can take months or years. Crews must stabilize rock faces, rebuild foundations, redirect drainage, and sometimes literally reconstruct sections of mountain. If multiple segments were affected within that newly mapped 100-mile risk zone, closures could overlap. That would isolate entire stretches of coastline. Local residents understand this risk intuitively. Many have seen landslides block the road overnight. They've watched crews carve new lanes into hillsides. They know this landscape is alive. But even long-time locals are surprised by how far the new flood vulnerability zone appears to extend. Environmental analysts say the concern is not one single catastrophic flood event. It's cumulative stress, small saturations, minor shifts, repeated strain. Think of it like bending a paperclip. One bend does nothing. 10 bends weaken it. 50 bends snap it. Coastlines behave the same way. So, what's driving these changes? The science points to a convergence of forces. First, ocean behavior. Sea levels along parts of the California coast have been rising gradually over time. Not dramatically year to year, but enough that storm surges now reach slightly farther inland than they once did. Even a few extra inches of reach can push salt water into soil layers that historically stayed dry. As salt water changes soil chemistry, it can break down certain minerals that help bind the sediments together. Over time, that weakens structural integrity along coastal slopes. Second, atmospheric patterns. Climate researchers tracking Pacific weather systems have documented shifts in storm intensity distribution. Instead of steady seasonal rain, the region is experiencing more clustered precipitation events. That means longer dry gaps, followed by sudden heavy downpours. That pattern stresses terrain. Third, geology itself. Big Sur's cliffs are composed of layered rock types, some harder, some softer. When water seeps into softer layers beneath a harder rock, it creates a natural slip plane. Kintore, the top layer stays rigid. The bottom layer becomes slick. Gravity does the rest. Imagine placing a heavy book on top of a wet bar of soap. It looks stable. Until it suddenly isn't. Fourth, vegetation cycles. Plants normally help anchor soil with root systems, but drought, wildfires and disease can thin vegetation cover. Without roots gripping the earth, slopes become more vulnerable to erosion and sliding. Individually, none of these factors guarantee disaster. Together, they form a system under strain. That's why experts are concerned, not panicked, but concerned. Concern in scientific language means conditions are trending in a direction worth watching closely. Now consider the worst case realistic scenario, not a Hollywood catastrophe, not the ocean swallowing the highway in a single night. Instead, imagine a season of unusually heavy storms following a prolonged drought. The ground is dry and cracked. Rain arrives fast and hard. Water rushes into fissures, saturating deep layers. Underground pressure builds. A section of cliff weakens silently for days. Drivers pass. Nothing looks wrong. Then one morning, a portion of slope gives way. Not a massive collapse, just enough to take part of the roadway with it. Crews rush in, the road closes. Traffic reroutes, repairs begin. But before repairs finish, another saturated section miles away shows signs of movement. That closes too. Now closures exist in multiple places across that expanded risk corridor. Travel slows, deliveries delay, emergency response times lengthen, tourism dips. Local businesses feel it. Residents must plan trips hours in advance. What was once a scenic highway becomes a patchwork of open and closed segments. This scenario has happened before in isolated stretches. The concern is whether the probability of multiple simultaneous disruptions is increasing. Scientists don't claim certainty, they claim probability shifts. And probability is what infrastructure planners pay attention to. So should you be worried? Here is the truth experts emphasize at Tradzi: there is no immediate evidence that a massive failure is imminent, monitoring systems along the coast track rainfall, soil moisture, slope movement, and groundwater pressure continuously. If readings cross danger thresholds, alerts can be issued. Preventive closures can happen before collapse occurs. That monitoring capability is crucial. Decades ago, such subtle changes might have gone unnoticed until visible damage appeared. Today, satellites can detect millimeter level ground movement. Sensors buried in slopes can measure internal water pressure. Drones can map erosion patterns after storms. In other words, this is not a blind situation, it's a watched one. What scientists don't yet know is how quickly current trends might accelerate. Will the expanded flood risk zone stabilize, continue growing, or fluctuate year to year? Natural systems are complex, coastlines especially so. They respond to ocean cycles, atmospheric oscillations, geological stress, and biological change all at once. Predicting exact outcomes is difficult because each factor influences the others, but uncertainty does not mean ignorance. It means ongoing observation. And that's exactly what's happening now along this stretch of California coast. Teams are collecting more data, updating models, comparing projections, watching for patterns, not because disaster is guaranteed, because understanding risk early is the best way to prevent it later. So, if you drive Highway 1 tomorrow, you might see nothing unusual. Sunlit cliffs, blue water, pelicans gliding over waves. The same breathtaking view millions have admired. Yet beneath your tires, beneath the asphalt, beneath the rock, forces are moving slowly, quietly, patiently. Landscapes are never as still as they look. The expanding 100-mile flood vulnerability zone near Big Sur is not a sign that collapse is certain. It is a signal that conditions are shifting, that the balance between land, water, and gravity is being tested, and nature always keeps the final vote. The question scientists are asking now is simple, not if this coastline will change, but how and how soon.